Hello friends, welcome to another lecture of mechanical vibration. The subject code of this subject is ME502 and this comes under 5th semester mechanical branch. My name is Ghanshyam Jawalkar. I'm assistant professor in SIRT and today's topic of vibration is harmonic analysis, and inside the harmonic analysis we will discuss the Lissajous figures. So let's start. First of all, what is the Lissajous figure? So, whenever we are adding two mutually perpendicular motions of a particle in which the amplitude are different and the frequency is equal to each other, or I can say that when the particle is moving in two mutual perpendicular direction with the same frequency and different amplitude, the curve which follows by the particle is called Lissajous figure. So for define the practical case, let us assume that the two independent forces acting on a particle in such a manner that the first alone produces a simple harmonic motion in the x direction, and this is given by x is equal to a1 sine omega t. So we have already assumed that there is a simple harmonic motion of the particle in x direction, and this is represented, the motion is represented by equation a1. This is a simple harmonic equation a1 sine omega t, and the second would be second would produce a simple harmonic motion in the y direction given by y is equal to a2 sine omega t plus delta, where delta is the phase difference. So uh, in the x direction the motion is given by this equation, and in the y direction the motion is given by this equation where delta is the phase difference. Thus, we are actually considering this superposition of two mutually perpendicular simple harmonic motions which have equal frequencies that I told you earlier, and the amplitudes are different and their phase difference by delta. The resultant motion of the particle is combination of the two simple harmonic motions. So, whatever be the resultant, this is the combination of two simple harmonic motions, which is uh, in x direction and y direction, or I can say that perpendicular directions. So the position of the particle at any time t is given by x comma y, where x and y are given by the above equations. The resultant motion is thus two-dimensional, and the path of the particle is in general an ellipse. The equation of the path traced by the particle is obtained by eliminating t from above equation. Now we can write sine omega t is equal to x by a1 by the first equation, and by the second equation or by the first equation we can also write cos omega t, that is under root of 1 minus sine square, or instead of sine square omega t we can write x square by a1 square. So this is the uh, these are the new terms which can be derived by the equation 1, x upon a1 is equal to sine omega t, and cos omega t is equal to under root of 1 minus sine square omega t, or instead of sine square omega t we can write x square upon a1 square. Now we have already seen that the sine omega t is x by a1 and cos omega t is equal to under root 1 minus x square upon a1 square. Now putting these values in equation for y, so in the second term we are putting the values, in this second term we are putting the values, these two values, so we'll get another equation. So putting the value of sine omega t and cos omega t in the equation which is for y, so y is equal to a2. Now sine omega t into cos delta, sine omega t into cos delta. As you can see, we are applying here the formula sine A plus B, that is sine A into cos B and cos A into sine B. And this is the formula, just we are extended the formula that sine A plus B, instead of A there is omega t and instead of B there is delta. So this is the equation y. So y is equal to a2 sine omega t, that is sine A into cos B, and cos A into sine B. Now putting the values of sine omega t and cos omega t in this particular equation, so we will get another equation, A2 is equal to x by A1 cos delta plus under root of 1 minus x square upon A1 square into sine delta. Or this can also be represented like this. This A2 can be come to this side upon uh, y. So y upon A2 is equal to x upon A1 cos delta plus under root of 1 minus x square upon A1 square sine delta. Or by rearranging this equation, we can take y upon A2 minus x upon A1 cos delta, and in the other side, the right hand side, under root 1 minus x square upon A1 square into sine delta. Now squaring both sides, so this is the squaring, we are squaring both sides, left hand side and right hand side. So this equation will write like this. Now we can apply the formula a plus b whole square. So we can get another term, that is y square upon a1 square, a2 square plus x square upon a1 square into cos square delta minus 2xy a1 a2 cos delta is equal to, now there is a the root, so root can be cancelled and we can get the power, we can get the square of sine. So 1 minus x square upon a1 square sine square delta. Now by rearranging the equation, we can also write this equation like this, where y square upon a2 square plus x square a1 square cos square delta plus x square a1 square sine square delta minus 2xy a1 upon a1 a2 into cos delta is equal to sine square delta. Now uh, we can take x square a1 square common from these two terms. So in these two terms, if we are taking x square upon a1 square common, so this in the bracket this can be cos square delta plus sine square delta, and we already know that guys, cos square delta plus sine square delta is equal to 1. So it will get just it will give the value x square upon a1 square. So y square upon a2 square plus x square upon a1 square minus 2xy a1 a2 into cos delta is equal to sine square delta. So supposed to be this is the equation for the Lissajous figure. Now this is an equation of ellipse. You can see that this is the equation of ellipse. Thus, we may conclude that the resultant motion of the particle is along an elliptical path. So when there is a two mutual perpendicular simple harmonic motions of a in x and y direction, so we will get a elliptical curve or elliptical figure, and this figure is called the Lissajous figure. Here x remains between minus a1 and a1, and the that of y remains between minus a2 and a2. Thus the particle always remains inside the rectangle defined by this equation. Okay, so we'll get the ellipse like this. So this is the elliptical part, and uh, uh, the value of a1 and a2 is inside a rectangle. Now there are three special cases. The two component of simple harmonic motions are in phase, delta is equal to 0. When there is a no phase difference in x and y directions, the motion of the x and y direction having no phase difference, so we will get a straight line which is passing like this. So we'll get a straight line which is passing like this. Okay. Now if the value of delta is pi, so we'll get another straight line, and this is like this. And if the phase difference between the two components, uh, simple harmonic motions, delta is equal to pi by 2, so we can get another ellipse, and the major axis is y, and major axis is x, and the minor axis can be y. So in this manner we are finding the Lissajous figure. We can draw the Lissajous figure. Uh, I hope you understand today's lecture, and which is about the Lissajous figure. And the Lissajous figures are the figure derived by the uh, by the simple harmonic motion of a particle in mutually perpendicular directions. So thank you very much.